So yes, what is coming up is a look at what goes inside a workspace and how the workspace is managed by the interpreter. And everybody's first question when I told them that's what I was doing was why? Well, because you've asked. That's not you. That's you've asked for how it works presentations of the interpreter. So that's why I chose this one. It really affects performance, what goes on inside the interpreter here. This is very much an us problem, not a you problem, of course. But although we've made it as fast as we can, sometimes there is some tuning you can do to make your applications go faster. And I hope that at the end of this presentation, you'll have some understanding of what it is you're doing when you're tuning it. So, disclaimer. I don't think there's any outright fibs coming up, but there is certainly a lot of simplification and skirting over some details, because otherwise we'll be here for days. So, what is the workspace? Well, it's a big contiguous block of memory which the interpreter asks the operating system to allocate. The interpreter itself entirely manages what's in it. The interpreter it tries to keep it small. It doesn't at any cost try and keep it small, but it tries to keep it small as is reasonable. And the workspace will shrink and grow from time to time, but it will never get bigger than max_was. So your max_was is an absolute upper limit for the size. So let's look at the initial allocation first of all. What the interpreter does is it reserves enough space in the computer's address space for the maximum workspace size. So we've got a huge chunk of reserved memory addresses so that nothing will get in the way. But we only actually allocate a teeny tiny workspace to start with. As of 19.0, that's 1/32 of max_was. And then what do we put in that workspace? Well, we put pretty much everything in the workspace. So your arrays, your symbols, your functions, the APL stack, everything is in there. And everything in the workspace is made up of a thing we call pockets. So a pocket in the workspace looks like this. In there are some free pockets. That means pockets which are not currently in use. And there are allocated pockets. They've got something in them. There's many, many more than I've shown here. They would be invisible if I did the right number. And there's lots of different types of allocated pocket, and we'll look at a few of those later on. So how do we allocate a pocket? If the interpreter needs a pocket, what do we do? Well, we just simply start from where we left off the last time, which is where that little arrow is. And we say to ourselves, are we pointing at a free pocket? And if we are, is it big enough? And in this case, well, we're not. So we advance to the next pocket, which we do. We can see there's a free pocket there. In this case, let's assume it's big enough. So we snaffle that space, and the bit that's left over becomes a new free pocket. And the next time round, we'll carry on from where the arrow's now got to. And this is quite straightforward and simple. Let's look at a workspace from the very beginning. So here we've got a big empty workspace. It contains a single huge free pocket. And our allocations start off very simple because there's all this free space. We just grab some space, grab some space. Each time we grab some, we make a new free pocket for the remaining space. As we go through, occasionally, in fact quite frequently, we'll free pockets. We no longer need those, so we'll see some gaps forming behind. And then we'll get to the end. And at this point, let's imagine we want this much space, but we can see that at the end there's not enough space, so we rotate round to the beginning again, and we keep going until we find a space that's big enough. And here we find one. So we grab that, the remainder becomes a new free pocket, we're done. So let's assume that we want another pocket that happens to be of this size. Well, you might be able to work out what's going to happen here. I go, oh, there's some space, but it's not big enough. So I go on, that's allocated, that's not big enough, that's allocated, not big enough. We go all the way around until we get back to the beginning. And we haven't been able to find anywhere for this. So we couldn't allocate any space for that pocket, so we're in trouble. But it's not yet necessarily a wasful. So what happens next I'll come back to, because I need to explain some other stuff first. Let's actually look inside some of these pockets, what we use them for. So a free pocket, the green ones, very simple. There's just a length at the beginning that allows us to jump to the next one. Everything else in that space is unused, it's just junk. And if we look inside an allocated pocket, there's a length field just the same as there was with a free pocket, and there's these two additional fields, this R and this Z, and then the payload, whatever is appropriate for that pocket. I'll come back to R. The Z field, Z stands for zones, and it's a single word in the workspace. It tells you what sort of pocket it is, and then the rest of it is pocket type dependent. And there's 15 major pocket types defined at the moment. So if we think about an APL array, how does that look in terms of pockets? Well, there's a regular pocket. In this case, the zones field tells us that it's a simple array pocket. It's got a rank of 1. And what I'm going to put in this array is the numbers 1, 2, 3, 4, 5, 6, 7, 8. I keep using APL expressions to show what's in them, but we don't store the expression, it's the result of the expression. So this has got 8 elements of 8-bit integers, because they're very small. So in the next field, we put the shape, which is 8, and in the next part, because they're 8-bit integers, we can squeeze all 8 of them into a single word. So they fit into the next word of the pocket. So that's what 1, 2, 3, 4, 5, 6, 7, 8 looks like in the workspace. If we look at another simple array, exactly the same as before, except there's a 1, 2, 3, 4, 5, 6, 7, 100,000, then we need bigger elements for those. They're all the same size, and we need 32-bit integers. So as before, we have the shape, but then each element now needs 32 bits, so we can only fit 2 of them into each word. So we need another 4 words for the remaining elements. And then when we have non-simple arrays, we have to use multiple pockets. So here we've got a non-simple array consisting of the 2 simple pocket arrays that we saw just now. So we have the 1, 2, 3, 4, 5, 6, 7, 8 as we had before. We have the other pocket as we had before. And then we have another pocket, which is a non-simple pocket, which has got a zones field which says it's non-simple, and it's got a rank of 1, and it's got a shape of 2, just the same as the others in the next word. But then instead of values, it's got pointers to the other pockets in the workspace. Okay. So I'll quickly do some other pocket types as well. We've got symbols, the names that you use, and I've deliberately missed bits out, but it's got the same general format: length, R field, and the zones, some stuff, oops, too soon, a pointer to the top level pocket of the value, and its name. And I'm going to draw quite a few of these, so I'm going to draw them more simply. That's the same thing, just for the going forwards. We've got pockets that contain your lines of code. So this is what you type into the editor, the individual characters. But what that looks like in the workspace, and this is the reason why, talking earlier this morning about preserving how source looks, the reason it doesn't normally look as you typed it is because we change it. So we've got a pocket, it's got the same initial header, it's got some stuff, but it's got a reference to the dictionary entry for the name tot. It's not a direct pointer, but it's close. So it's a very simple relationship between that word and the dictionary entry for that value. It's then got a token for the arrow that's there. There's no spacing in there. It's then got another reference to something in the symbol table. It's got the plus token. It's got another reference to a symbol, like so. And each of those symbols exists at the time that you fix the code, but they've got no value. There's no pointers from those symbols to any value yet. And another very important one is the stack. So let's have a look at what happens when we run this simple little bit of code. We enter a function, we create 2 separate pockets, one to say that we're inside a function. The other is this thing we call the shadow block, because in this function we've got a localized R and we've got a localized A, but there's only one R and one A in the whole of the namespace. So what we have to do is park the old value in a shadow block. So that lives there. We then run through this code. we've got an each, so we need somewhere to keep track as we go through all the elements when we do the each, and there's two elements in this particular case. And then when we do the each, we then run into the plus slash. So we've got to run through all the elements when we do the plus slash. So we have another stack frame for that. And then when the plus slash finishes, we go back to the each, and it's another one. So we go back into a plus slash, and then that finishes, and the function finishes, and we're done. Okay. Right. Now, fundamentally important thing is the reference counts, that R field, which I missed out. So fundamentally, the R field is simply a number of references to any one pocket. In this picture, which is close to one I showed you before, all of the references are one. There's one thing referencing each of those pockets. But if I assign that, well, run this code, B gets A, I don't create a whole new set of pockets. I just point again at the top level pocket, and its reference count goes up to 2. If I expunge A, then that pointer goes, the reference count goes back down to 1. And if I expunge B, the reference count goes down to 0. And at that point, we can free it. So it disappears. And at that point also, the other pockets' reference counts go down to 0, so they can be freed as well. If we have this expression, we know what IO to 8 looks like. We saw it before. We don't create that twice. The topmost pocket just points to it twice, and it has a reference count of 2. And then we name it, so we've got a reference count of 1 to that pocket. So the point about reference counts is that they save space. You saw I didn't need to keep duplicating everything. And they also make assignment very fast. And because of the way APL works, it would be impractical to write an interpreter that didn't use reference counting. But reference counting has some very interesting effects on performance. So if you've got a pocket with a high ref count, you can't modify it because you would be modifying multiple things. So if we have this little bit of code here, we do A gets IO to 100. We create a pocket with the values 1 to 100 in. You would not believe how long it took to do that. And we reference it from the dictionary, from the symbol table for A. And then when we do the addition of 1, we create a new pocket, and we add 1 to all of the elements. So we've got 2 through to 101 referenced by the symbol table for R. We had to create 2 pockets because if we didn't want to change A. But if we had this code instead, we could create the IO to 100 pocket, but the only thing that's referencing it is in the middle of this expression. We can update that in situ. So we can change that value, and the symbol R can point to it without having to create a second pocket. Now, in this case, I did some timing, and that happened to be 20% faster. It obviously varies on what you're doing. But as I say, you've got to have a low reference count to be able to do that. And there's one other thing to talk about. I've talked about free pockets. They are not what we call in Dyalog garbage. Garbage occurs when there are reference loops. So you've got a pocket referencing a pocket, and ultimately you come back to the same pocket. And you can end up with a situation where the only things that are referencing those pockets are themselves. There's nothing else referencing them. So they are, in fact, unused, but they've got a reference count of greater than 0, so they're still there in the workspace. Now, traditional APL can't create those. If you think about that non-simple pocket that I had before, where you had a outermost pocket referencing an inner one, if that one referenced back to the outer, you would have an infinitely deep array. So they just don't exist, but OO features can cause them. But you'll be very glad to hear that I'm not going to talk at all about how we deal with that, because that will take a whole new presentation. Okay, so we know a little bit what these things look like now. We can come back to this place where we got to before, where we run out of space. So what do we do now? Well, the first thing is we do pocket compression, which we call squeezing, and we look at all of these pockets and see, can we make them smaller? So here's the pocket, one of the pockets that was in there. Let's have a look at what might be inside it. We're saying it's a simple array, rank 1 of 64-bit doubles, but when we look at the values, they're all small integers. So we can shrink that pocket down to 8-bit integers, and it's smaller. What happens then when we put that back in the workspace is that we get an extra free space where it was. And we can do that with all of them, so we get more green space now because we've shrunk as much as we can. And then after we've done that, we squash them all down to the bottom of the workspace. We call this compaction. So they all move down so that we've now got just one free large pocket. And when we've done this, we also have a lot of pockets which are all together, all allocated, all at the beginning of the workspace. And we find that pockets that live for a long time, or indeed sometimes the entirety of your application, all congregate at the beginning of the workspace. And what we don't want is, as we go through looking for space, we don't want to go from the end back to the beginning and walk through all of those pockets. So we keep a separate pocket pointer to where the first free space is. And this group of allocated pockets at the start is called the sediment because it tends to settle there. So now we've done that, we were asking for this much space and we can quite simply get it. Now imagine we did a free here and it was earlier in that sediment. We have to make sure we keep that pointer up to date. Let's do another allocation. Now we want another one. Well, let's see what we do. We can't fit it where the orange pointer is, so we rotate round to where the sediment pointer is. It won't fit there. We get all the way around. We get back to the beginning. It didn't fit. So what do? Well, we do what we just did before. We compact and we compress. But there's still no room. So now, you remember, we only took a 32nd of the space we had. This is the point where we ask for more memory. And now we can put our pocket in there. So this pocket allocation algorithm is incredibly simple. It's very fast, and everybody who looks at it thinks they can do better. And no one has. we very nearly did an 18.0, but we won't talk more about that. It didn't work. We had to put it back the way it was. Right, so I've only showed the workspace getting bigger. When does it get smaller again? Well, the main time is when you do a quad WA. So it does the compression and compaction. It then looks at the size and adds a bit, what it thinks is right, and says, right, that's how big the workspace is now. So there are some useful tools, well, hopefully useful tools, that you can use with this to see what's actually going on, now that you have a bit of an understanding about what's going on there. There's this iBeam 2000. This can tell you various things, like the actual number of free and allocated pockets in your workspace, the number of compactions that have happened either since the start or since you reset the counter, the size of the sediment, that group of allocated pockets that sort of sits at the bottom of the workspace. It will tell you how big the low and high watermarks of the actual allocation size. Again, you can reset that and monitor it. And you can actually set the minimum and maximum as well. And the other thing it will do is give a WA without compaction. So it's a very fast quad WA. It just totals up the size of all the free pockets without making any other changes. There is another iBeam 2002, which is a quad WA, but allows you to say how much extra space to leave. So this is possibly quite useful if you find that you do a quad WA, reduce the size, and then immediately increase it again, which of course is time consuming. You can tell it to leave a large amount of space instead. So whenever we talk about iBeams, we always say, how did we come up with that number? And to answer this particular one, we have to go back to the ancient Romans. So why 2000 iBeam? Well, ancient Romans, apologies for my Latin. But if we look at the MM iBeam more carefully, we can see that it consists of two M's, which stand for Memory Manager. So there you go. I can't remember who's like. Was that you, John? It was John, yes. Good. So, the workspace. I've done this much quicker than I expected. Have I missed something? Everything in it is a pocket. Pockets are ref counted. Pockets are allocated using this rotating fast first fit algorithm, which I think the name is fairly self-explanatory from what you just saw. And we compress and compact only when we have to. And we increase the space actually required of the operating system when we can't compress and compact anymore. And we've given you various different things to monitor what's going on and control it. Thank you.
All right, thank you everybody. Thank you, Richard. We'll just need